Okay, thank you very much for the invitation. Yeah, so I'm research director at Inria until September, and then I will be professor at Ecole Polytechnique, so I put the few affiliations. And so today I'm going to talk about data assimilation in shape spaces. So I'm pretty sure that the presentation will be too long. That's always the problem with me, so I apologize for the inconvenience. And
it's already too long.
And typically, you will see shapes pretty much everywhere, but I will discuss the problem of data assimilation in shape spaces just at the very end of the presentation. So basically, it will be long, and if you want to be interested from what I'm saying, you will have to wait until the end. So basically, the subject about data assimilation is so the keyword nowadays about data assimilation is not data assimilation, is creating digital twins. So that's the new fancy word for all topic which correspond to coupling physical a model for a physical system and data together in order to create a virtual system that's closer to the physical one. So typically, it is a white paper from the Academy of Sciences in the US saying that if we want to talk about digital twin, a digital twin should couple model and data. Okay, and that's typically the purpose of data assimilation when you come from the modeling world, which is my world, typically. So what I'm going to, sorry, again, just otherwise you'll not see any.
You can just click OK.
Title. So I will show you my vision of digital twin, which is model-centric vision. So I will start from the models and show you how to incorporate data in them. And the particular point of this topic of this seminar is how to integrate shape data. So to start with, let's take the time to have some example in mind. Okay, so in my group, there is a lot of people working on cardiovascular mechanics. So typically in mechanics, in cardiovascular mechanics, we try to simulate a heartbeat. So typically this is the two ventricles. Okay, and for that, you develop complex models for computing the displacement of the domain. So U is typically the displacement of the domain. And for that, you have a very complicated formulation of elastodynamics in large deformation. Okay, we don't care today about that. Just the idea is that you have to solve a PDE system just to compute this displacement, and this displacement is Lagrangian. Okay, saying that you follow material points. Okay, so that's typically how people in biomechanics works to compute this kind of model. And on the other side, you can have observations. So typically, if you go to an imagery system, then you can get some sequence of images for the cardiac heartbeat. So this is the long axis, this is the short axis typically. And from that, if you have several short axis sequence, then you can segment them and recreate the shape of the epicardium and endocardium of the heart. So typically, an observation from this imagery system, one observation of the heartbeat is these two surfaces that are moving. So that was the first example. And the question is, how can I assimilate such type of data in such complex model? Okay, let me give you a second example with reaction diffusion problem. So for the heart to contract, you need an activation, and this activation is an electrical activation. And this is typically a simulation of this electrical activation propagation on the heart. So this is the atria, this is the ventricle. The typical model for that is a reaction diffusion problem, W0. So again, complex PDE problem. Okay, and there are many models like this. There are also models where you just try to follow the front of the propagation. And if you do, in order to do that, you can do asymptotic analysis around the front. So you create a new variable around the front and just try to follow the front. And if you do that, you end up with different form of model in Lagrangian or Eulerian. Lagrangian, you will just have this kind of contour-based model, or in level set formulation, this kind of curvature-based propagation. Again, you will see we don't care about the model. The question is more to see that typically in the problem that I'm looking at, there are always some kind of shape structure somewhere. And what are the observations for such problem? Typically, in the lyrics at Bordeaux, what they do is to record on a vest a set of electric signals that they call body surface potential. So that's the body surface potential, and that's the time evolution of this signal. If they do some imagery, they can get the geometry, and from that, they try to recompute what they call time map or maps of the electrical activation. So this line are the time where the electrical activation has passed or not. Okay. This is with the synthetic pictures. That's how it works with real pictures. So that's with real data. So the geometry is like that. The signal is like that, and what they get is something like that. Okay.
I like that.
Sorry.
I like that.
Yeah. And typically here it's very noisy, and they can't reconstruct a map everywhere. Okay. Maybe last, but not least in this presentation, and not yeah.
When the geometry you have snapshot, or you are the times the geometry will have different time space?
Here?
Yes.
Here typically, so for the electrical potential, typically the classical model that is used consider that the heart is not moving for the electrical activation to develop. This is, I would say, not completely fair, but not so unfair, because the activation has a time scale which is much faster than actually the mechanical deformation. Okay. So typically you only need one geometry, and this will depend of time. Okay. And so here the geometry is fixed, but typically what moving is actually the front. Okay, so, and last example, for fire propagation models, just to say that actually we are not working only on a cardiovascular system, but from what we have developed on the reaction diffusion problem, people from Fairfax ask us questions about using the same type of technology for fire propagation model. So in a fire propagation model, typically you have this kind of econal-based model, which corresponds exactly to the same asymptotic formulation that for the reaction diffusion, that you can solve like this with the level set version, or like this, where typically at the end you can rewrite it more like this, with the shape moving with respect to a velocity field along the normal. Okay, and they use at Fairfax they use either this type of formulation to discretize and simulate, or this type of formulation where they use the Fermat principle to follow the evolution of the. Okay. So again, quite complex models and observation. So here I give you two examples. This is a controlled fire where they have a lot of data. So real data, but controlled fire. And typically what they follow here, again, is the map of arrival time of the fire. So that's the true data, and that the segmentation of the corresponding time of arrival. Sorry. And here, a more complex case, so the real fire Yosemite, typically, and again, maps of the fire propagation here in color for different times. Okay, so for all these problems, the question is, can we design strategies to couple such complex dynamical system with such shape data in order to provide what we will call, okay, to get money for grants, a true virtual twin. Okay, and typically the object to do that is normally is data assimilation. So data assimilation is a whole topic that comes from the 60s and developed during the 70s with computational aspects. So it's a very old subject. So what is new? I would try to show you that there is still open question on this subject, and in particular, this open question comes from the fact that when you want to do that in spaces that are just not Rn, then it can be difficult. Okay, but let's start with Rn. In order to present you what is data assimilation, let's start with a very simple dynamical system. Okay, so dot x means the time derivative of x. Okay, so you have a system like this, a class of system. Okay, because it's parameterized by the initial condition and the source term here. And on this class of system, you see one solution of this system, which is called the physical solution. Okay, so it's called X change here, and on this X change you get observations. So you measure something on one trajectory of this system for a source term and an initial condition that you don't know. Okay, so you don't have these guys, so you can't simulate the true system, but you have this. Okay, and the question is how to reconstruct the most plausible solution that is compatible with these two guys. So the way to do that, as often, is to define some criterion to be minimized. Okay, and so in that case we consider a linear quadratic criterion. So you penalize the initial condition from an initial case. You want the solution that you want to compute should be close to the observation, and the source here should be small. Okay, because you imagine that this guy should be a perturbation of the true system. Okay, if it's not a perturbation, then you get an a priori on that, and you scale the perturbation. Okay. Yeah.
A and B are known.
Yeah, A and B are known in that case.
And they are time independent.
No, they can be time dependent. They are time independent for the purpose of the slides, but they could be time. And C is known. Okay, so still model centric. So in model centric, it means that you know how to model the physics and you know how to model the observation procedure. Okay. But in fact, if we want, we can discuss that at the end. If I make this guy, if I want to make this guy uncertain, I can make it dependent of parameters and then add the parameters in the variables that I don't know. But I will not discuss that during the presentation. Okay, so how to minimize that? So basically, the idea is to minimize this criterion under the constraints of the dynamics. So in order to do that, you develop, you set up a Lagrangian where here you have a Lagrange multiplier that take into account the fact that you want the system X to follow the dynamics. And then you compute the, and you define the good trajectory as the inf sup of this Lagrangian, and the idea is to compute what we call the optimality condition, and you get this system. Okay, so this comes just from, so you want that, so for that you compute the derivative of L with respect to each variable, you put the derivative equal to 0, then you get the optimality system. Okay, so it's classical linear quadratic optimization under constraint. And you get this guy. Okay, in this guy, that's the trajectory that you want to follow. Okay, but it depends on the Lagrange multiplier. And the Lagrange multiplier is given by this equation. What is difficult here is that this solution starts from 0, as it is dynamical system, but this guy starts from t. So it goes backward. So typically, this system is called a two-end system in the sense that it's not a Cauchy problem anymore. It's not from 0 to t. It's coupled 0 and t. Okay, and you have to solve that all together to get the trajectory. As soon as this is too difficult from a numerical point of view, what people do typically is to solve that iteratively, okay, by iterating between this and this. Okay, so you relax a bit the problem and you iterate until convergence. Okay, so that's what people, most of the people do, and that works pretty well, and it's called variational data assimilation, and it's nice. Oh, so typically, the idea is to find an iterative way to solve these two ends problems by the succession of two Cauchy problems. This one forward and this one backward.
Okay, but in the end, you want to solve the same problem.
Yeah. At the end, at convergence, you solve that. And actually, if you have,
it's not simpler than the initial problem. Is it? Can we go back one step?
Yeah. No, it's the same problem. I just rewrote it the same equation. Yeah, it's the same equation.
So what would you say that it was simpler?
No. If you want to do it, if you want to solve the coupled system, then what you need here is to solve a value, a boundary value problem in space plus time. Okay, and so that for that you need to, for example, if this guy is 3D, then you have to create like 4D elements and solve it as a 4D problem.
You resort to some sort of method?
Yeah, exactly. To solve this value problem. Yeah, it's exactly that. But since these guys should be big, okay, so the X here at the end can be very big. So typically, people resort on an iterative procedure to solve this guy. Okay, and that works, and it works, and it's nice. And typically, that's typically the thing that I don't want to do. Okay, don't ask me why. I'm starting my career in trying to avoid to solve that. I'm not sure that I make the good choice, but so I will discuss for the rest of the talk two other methods.
Yeah, because the first thing is just the usual way when you want to solve geometric problems.
Yeah, exactly. Yeah. So what I don't want to do is to do the usual way.
Okay, but can you explain a little bit more?
Yeah, after the talk, okay? Because I believe because when it's non-linear, it's not so cheap to do that. But for now, it's still linear, so it's not a strong argument. But non-linear is not so cheap because the problem is well known, and I prefer to look at problems that are not well known. And I think it's a good idea in research. Because, and that's the true reason, is that the method that I will try to show you will be sequential, so will remain Cauchy problems. A bit more difficult to solve at first sight, but actually the good point is that at the end, even for very complex systems, we will keep the fact that we can follow a model and then correct with observations. And that's very nice when you have people from the engineering community that say, I have a very complex code, and what I don't want is to solve this guy. Because I can't do it. What I can do it is actually solve my problem. For you, it should be a black box. Even if I know what is in it, it should be a black box. Okay, and what I want so that's what people from the engineering community tell me. What I want is that you interfere with my code as less as possible. Okay, but we can discuss that at the end. There is still a matter of choice in what I'm showing. Okay, so one way to decouple this two-end problem is actually to solve what is called a Kalman filter. So the Kalman filter is given by these two equations. So in this problem here, I'm solving a Cauchy problem only from x0 for x. If I can compute this pi guy, and this pi is given by this Riccati equation, starting from also an initial condition. So if I solve these two initial condition problem, I can prove that actually at the end of the time window, the solution of this guy will be actually given by this guy. So the important part is actually that the Kalman solution at the time t corresponds to the solution of this guy when the S here is equal to t. Okay? I will show you an illustration to set up the mindset about that. But typically, how you prove that? What you prove is that typically x and pi is a way to decouple these two. Oh, sorry, that should be a bar here. These two guys. So these two guys are coupled, and typically x and pi is a change of variables that help you decouple the system. Okay.
What is the dimension of the half example? By
1,000 of degrees of freedom to millions. Okay? So curse of dimensionality will be a huge problem in all the talk. Okay? You already have seen. Okay, this guy is a matrix because it follows the Riccati equation, and in the space of x. So if you have 1 million degrees of freedom, this is 1 million square values. Okay? And that's why in the 60s, it was developed on a theoretical aspect, but not so used in the data assimilation community with respect to this guy. Okay, let me, just to show you how it works, let me show you this illustration. Okay, so you start with the true trajectory that you want to follow. You don't know this guy, so you start from the initial guess. You start from here. And you want to use the observation that you have here, okay? So typically, you set up your optimal system, and if you do the iterative procedure, after convergence, you get there, okay? You don't get there because you don't have a lot of observations, so you don't have a lot of things in your criteria to overcome the fact that you start from here. So you get there. So what Kalman says is that if you solve the Kalman solution, you get already there directly. Okay? But at each time, Kalman gives you only the last point up to this time. So if when time grows, the Kalman try to always follow the last value of your time window. As observation increases, you get more and more observation, so you expect your minimization procedure to be closer and closer to the true solution, and Kalman continue to follow the optimal trajectory. Okay, that's the spirit. Okay, and this trajectory is called the dynamic programming approach that solves the optimization problem. Okay, if you want to remind one thing from this seminar, you can say that if we want here to go to the bookstore or the coffee or the restaurant over there, you can try to planify the whole trajectory. Then you do variational optimization, or you can just go outside and follow the signs. Then you do dynamic programming. And typically, under suitable condition, that there is enough sign outside, you achieve the same optimality problem. Okay, that's the spirit. So you follow the optimum up to time t. You hope that when t increases, you get to the true trajectory. Okay, that's the dynamic programming approach. Okay. Let's move to something which is very important when we want to do a simulation, is the fact that actually all dynamical systems then are discretized, time discretized. Okay, so imagine that you have a time discretization of the problem before, and so you end up with this system. So here now it's just a sequence, and on this sequence you have observation. Okay, then you discretize also the criteria. Okay, so you replace integral by sum. You replace integral by sum here in the Lagrangian, and you do the optimality system, and you get this system, which is again a 2n problem in that sense. And the same theory applies, so that basically, in order to avoid to solve this, you can define a guy which is exactly the optimum at time n for a criteria up to time n, and this guy follow a time discrete system which is made of two consecutive steps. Okay, let's call a splitting time scheme for people who do time discretization, made of correction plus prediction. So the combination of one correction and one prediction corresponds to one time step. Okay, but in each time step, you can divide correction and prediction. What the correction does, the correction actually takes into account the observation to correct the trajectory, whereas the prediction only follow the dynamics. Okay?
Can you explain how the computational order or the two strategies?
I will. Okay? So typically, when you do that, that's exact on a time discrete setting, okay? And it corresponds to doing something like that. So you start from there, you correct to take into account the observation, then you follow the model, you correct, you follow, you correct, you follow, okay? And the blue trajectory, which corresponds to only the correction point or the prediction point, should converge to this value as time goes to infinity. Okay? So, from the computational point of view, if you want to do this discrete time setting, the only thing that you need is to be able to compute this matrix, okay, on a finite dimensional space. Okay, if you can do that, that is very easy. The problem is to solve this guy. Solving this guy is not so difficult from a discretization point of view. What is difficult is actually to store this guy, because this is a full matrix on the system. Okay, so here you do iterative procedure most of the time. So you solve something that is quite heavy in terms of numbers of iterations, so it takes time, and here it takes memory, basically. Okay, so the burden here is memory, the burden here should be time.
Okay. To be clear, like if you come back to the next slide.
Yeah.
So let's say X, it's like the state of the heart at time t. And what you're saying is that, okay, you start from the initial guess, which is X0 hat. Then progressively you say, oh, it's better and better and better.
Yeah.
But then you end up with X5, which is a very good approximation of the state of the heart at time 5. But then obviously you're going to, at the end, shoot back the equation because you're interested in the whole state.
It depends. Yeah, but it's also very strong drawbacks of dynamic programming is that if what you care about is this guy, then you don't have it.
Okay, you cannot just simply put back?
In most of the PDE problem, you can't go back in time. Okay, so you don't have it. But there is lots of systems where actually you don't care about that. What you care is the trajectory. Okay, so if this part is short enough, then you don't care because from there you can follow the trajectory. If you imagine that the heart is quasi-periodic, actually you really don't care about this guy. What you care is this guy because it's a quasi-periodic solution of what is going next. So if I want to do monitoring for the cardiac system, I don't care about what was the state 1 minute ago. What I need is the state today. And it's the same for weather forecasting. Well, in weather forecasting, you use the data from the last 2 weeks, okay? It doesn't work, so, but you use the data from the last 2 weeks, okay? And you don't care about the weather 2 weeks ago. What you care is about the weather today.
There is no, sorry, there is no way to do that because I think it's.
There is ways. There is ways.
Either Markov model or
Yeah.
the failure.
Yeah, exactly. So typically, there is way using the adjoint variable you can go, but actually it's pretty expensive.
Yeah.
But there is way.
That'd be good.
Yeah.
Good, but you will need to store
Exactly.
something along with all the.
Exactly. What you need is to store basically the Riccati operator during the whole time window, which is already, it was already expensive, and then you need to store it to go back. But okay. And just to conclude, the X here will be some kind of approximation of the displacement at different so xn. Okay. Okay, that's just to answer your question. Okay, if you Wikipedia Kalman filter, it's not what you find. Okay, if you Wikipedia Kalman filter, what you find is that. Okay, so typically the same algorithm with a complete different interpretation, saying that actually in the correction term, the x here should be the conditional expectation of the state with respect to the observation up to time n, and the pi here should be understood as a covariance. So from now on, I will always say covariance for this guy, even for I presented you with a Riccati. And then the n plus 1 correspond to the conditional expectation of the x n plus 1 and up to observation to time n. So what is very important is that in these two steps, here you go to n up with observation up to time n, and here you go to up to time n plus 1 with observation up to time n. And that's why you see something like that. Is that when you are here, you don't take into account the observation, and then you take into account the observation. And what is very nice from an engineering point of view is that this part, you can tell to the engineer guy, just follow your model. You don't care about what I'm doing, okay? Then I will correct to take care about the data. Then you cheat a bit, because then you will have to announce him that actually he has to do something with the covariance, okay? But as a first step, you can say, it will work with any type of model that you have, okay? That was the spirit. Okay. Okay, so that's when you do discretization. Does it work for PDE? Is there any theory for the PDE? The answer is yes. It's just more complicated in the sense that you have to define a meaning of that. So the first difficulty is that you can't use X anymore, because for PDE, X is already used by the spatial variable. That's the most important part of that slide. So you have to change the notation and use Z instead of X.
But for the third coordinate,
x1, x2, x3. And then typically the rest is the theory exists from the 70s. Typically, you can do it with the theory of Lyons-Magenet's solution for PDEs or semi-group theory, and typically you end up with the same type of proof. It's more complicated, but the spirit is the same. Okay, so just to tell you that there is a theory for the PDE case that is compatible with what we have seen in the discrete case. Let me give you one example for the fire propagation. So the fire propagation should be some kind of AGB equation. But what you can say is that just assume that actually the fire is not propagating too far. So you can change the model and say, let's consider a small propagation fire. As in mechanics, we can do small deformation model. So a small propagation fire should be something like that. Then the model is linear, and you can apply the theory before, and you will get something like that. So in black is the target trajectory. Here it will be what we call the free run. So you start with the wrong initial condition and the wrong source model, and you will see the trajectory that you get. And in blue, the Kalman estimator. And you see that, so basically you start from the same, but then you pursue, okay, you catch up with the true trajectory. Yeah?
But would you say it's fast enough to be tunable for a low data regime when you don't have many observations?
No, basically it scales very well with the data that you have, because typically you still follow the Cauchy problem. Okay?
And also, so maybe you said it, but I was looking at the slides. So my understanding was that you're trying to infer X from a low dimensional observation CX, but with forest fires, like
no, yeah, no. Here
exactly
you see here C is identity, so pretty much you see everything. So it's a super simple cases where you have total observation. Okay.
So in real life, you just have the observation, but it's the same.
Yeah. For the heart, you have clearly something which is a low rank observation operator. For the reaction diffusion problem, since you only follow the contour of the, you have also a low rank, etc. But in that specific example, it's a very easy example.
So just to make the connection with practical situation. So here you assume that you know more or less everything about the parameter.
Yeah.
But
for 1 hour.
Okay, easily correct, or is it?
Not at all.
No.
But okay. So if you need something to believe me. So if you have parameters.
But I mean to get for files.
Yeah. If you have some parameter, imagine that the system now is something like that. Okay, but you don't know this guy. Okay, what you can do is you can say, let's add this equation. Okay, and now for x theta, I go back to the same type of problem. One difference is that now the system x theta follow nonlinear dynamics, because most of the time theta here enter as a linear system, but then the system of x and theta is at least bilinear. If you can set up the same problem for nonlinear system, then you can imagine that you can do that. Okay? Actually, for the heart, pretty much all the examples that I've done in my career are about parameters. Okay, so it works, but yeah. But then it's one notation more, and it's already pretty heavy in terms of notation, so I decided to not talk about parameters.
I just want to understand if this is some kind of open problem.
No, you can do it like that. But then it's even bigger in terms of dimension, because you decide to the state is now x plus the parameters of your system. Okay. Okay. So can we do the same thing for nonlinear system? Okay. So here now the dynamics is nonlinear. It could be dependent of time either. Okay. Just to simplify it. So F now is nonlinear and H now is nonlinear. So you do the same. You write the same criterion to be minimized, and you can do the optimality condition, the Lagrangian and optimality condition. The question is, can we get the equation for the dynamic programming approach? So to do that, the idea is actually to define a value function that corresponds to this criteria where you fix the point where you arrive. Okay, so you decide that the value function at x corresponds to the minimization of this where your solution arrive at x. Okay? When you do that and you do a Bellman principle on this type of function, you get that the value function follow what is called a Hamilton-Jacobi-Bellman equation. Okay, so it's a forward problem. It starts from 0, and you have to solve that. Okay, I see that you are already starting to say it should be pretty expensive, and it is pretty expensive. Okay, it's even super expensive. Here there is a real curse of dimensionality in the fact that the problem is x here belongs to the state space. Okay, so you solve the AGB equation in a space of 1 million of degrees of freedom, and then you can define a guy by just computing the minimum of this value function. And in fact, what you can prove is that this guy follow a dynamics like that, which has the same structure as before. The only difference is that here you have the tangent of the observation, and here instead of pi, you get the Hessian of V, the inverse of the Hessian of V. Same structure. Okay, this structure that we call sequential form, and you can prove that this guy at time t solve exactly the optimal problem corresponding to that. So the same theorem. Okay, I will skip that, but just to prove you that it works, one way to see it is actually to go back to the linear quadratic case and say, okay, when f and h are linear, what happens? In fact, you can prove that then the value function has this structure where pi and x are given by the Kalman curve. So in the case where everything is linear in terms of dynamics and observation, then you prove that the value function is just a parabola that evolves through times, but it's just a parabola. And what you want to follow is the minimum of this parabola. Okay? And the covariance gives you the extension of the parabola around the minimum. Okay? But once you have that in mind, what you can do is to say, if I don't want to solve the AGB equation in a 1 million degrees of freedom system space, maybe I could take quadratic approximation of this value function as parabolas and just try to find the best parabola that fits with the value function through time, because what I need is just the minimum and the extension around the minimum. Okay? And that typically give you approximate version of the nonlinear filter, which are called the extended Kalman filter, which is very well known. Actually, we prove that there are corrections to this guy to be exact with respect to the quadratic approximation, and so we developed recently a new version with correction terms, but we don't care. So basically, what you have in mind is that what we want to do is not to solve the AGB, but just to get the parabola.
By doing so, do you have any ground case, question ground case that you will going to achieve? What you will want to achieve?
Alors, the question is, so it's still ongoing work to prove the. Okay, so there are proofs. There are all proofs of the fact that this guy can converge to the good can be a good estimator. The fact that the value function could be approximated at that is still open, but we believe that it's open because it was wrong, because the good version should be that. So it's still an ongoing work. So maybe next year, if you reinvent me, I will be able to but typically that's the idea, is to go a step further and to prove that with estimation error.
But what are the hypotheses of the dynamic in order to make to obtain such a result? Because it cannot work for any.
So typically the proof that we are trying to do for now corresponds to very simple bilinear dynamics, so a bit like that. And on that, it's still very difficult, and it's very recent results from colleagues from Graz to prove that actually the value function has enough regularity to define the estimator with the form like that. Because typically, AGB equation is not C2 normally. Okay, so it's just continuous. So you have a weak existence of a weak solution in the continuous space. So typically, this should not exist like that. Okay, but in certain situations, in the linear quadratic case, it's the case, but it's also in perturbed situation, it's also the case where you can prove that actually this can be C2. In that case, you can prove that this exists, and then you can pursue the errors in the estimation. But yeah, no, but it's huge work. It's huge work. Yeah. But then numerically, it works pretty well. But that's not an answer for sure. Okay, should we do that on a discrete level? The answer is yes, and you do exactly the same. First, you discretize your dynamics. You write, so you take the discretization that you want. Then you have also discrete observation. You discretize the criterion, and you define again two versions of the criteria, where basically you go up to time up. You take the observation up to time n for a dynamic going up to time n, or you take the observation up to time n for a dynamics going up to time n+1. The same spirit. Okay? That's something I've done some years ago, and which was also proved by Keener. And typically, if you define these two guys, you can prove that you have some kind of intertwined dynamics between these two value functions. One is n plus, one is n+1 minus. You see that this guy depends of the previous one minus, and this one depends of the previous one. But this corresponds to one-time step, basically. You just have two steps in one step, okay? And once you have that, you can define the x plus or minus as the minimum of this value function, and you get an algorithm like that, where you see a correction and then a prediction. The correction only used the observation, the prediction only used the dynamics. Okay, so I like this structure where you use the data, use the model, use the data, use the model again. And what is nice is that actually, yeah. So the only difficulty is to solve this guy, the value function. Okay, so that's super hard, but we still have tried this a bit for very small dimension system, and it's already an open problem to solve that in small dimension. So typically, for now, the challenge is to be able to solve it in dimension 10. Okay, that's already something. Okay, so it's not helpful at all, but it's very nice to try. Okay, and for that, with Nicolas Papadakis last year, we decided to use KOPS to actually solve the difficult part of this equation, which corresponds exactly to enough convolution of the cost after the correction, where you go back to the characteristic of the model. So if you can solve half convolution in high dimension, then you can solve this equation. And this part is easy, actually. So we decided to do that. And it's still ongoing, but it's not a problem of chaos, it's a problem of me. but it was pretty well for the first test that we had. Okay, and we were able to go up to dimension 5, typically, which was already nice.
What is chaos?
Okay, sorry, chaos is sorry. Yeah, and then one other possibility is actually to remind that actually the half convolution is a solution of a AGB equation, and so you solve this AGB, which is pretty expensive, but you can. As this is pretty singular, what you can do is to do some kind of vanishing viscosity version of that, okay, and then you solve that like this. And typically, instead of solving that, you take the Hopf-Call formula by just considering epsilon log of exponential of the value function, and so you get back to a heat equation. So if you are able to solve a heat equation in a very high dimensional space, then you can solve the problem I show you before. Okay. Okay. Can I get back to the Kalman estimator? The answer is yes. If you say that the function here is linear and h is linear, you get back to the Kalman estimator. Why? Because you prove that in that case, the Vn plus and Bn plus 1 are just parabola around xn plus and xn plus 1 minus with an extension which corresponds exactly to the covariance. So at the discrete level, you get exactly the same results that at the continuous level, which I think is natural. So typically, and then if you want to do it for nonlinear system, the idea is to perform the same kind of quadratic approximation, but at the discrete level, and you get back to the extended Kalman filter, which is very well known and used, okay, or the new version that I'm trying to develop, where actually I don't miss certain of the terms that are here, that I can discuss with you after the talk. And for the prediction step, actually the Kalman was, the EKF was right. I believe this is wrong, but that's what people do. Okay, so pretty much we have everything we want to try it. But, okay, huge curse of dimensionality, the value function, okay, you don't expect to solve it, but even for the covariance, it's a very big operator. And then what we don't have until the thesis of Gael was to have this. We have something for nonlinear system, but not on manifolds. So the question is, can we define something on manifolds where typically we can have enough structure to define something for shapes? Okay. So until the beginning of Gael thesis, what we have done in the team was typically to try to avoid to solve this problem because it was too difficult to solve for shapes. Okay, so okay. So and for that, the idea is to weaker a bit what we want. And so, if you remember that the Kalman filter or the Mortensen filter has the objective to get a trajectory like this, then you can say, okay, maybe I don't care about computing the covariance operator there. Maybe I can put some very simple operator that are cheap to compute and that do pretty much the same job like this. If you want to do that, you have to design it model by model. Okay? And so my scientific statement was, give me money until the end of my career, because for each model I will design for you one particular guy. If I change model enough, then I will have enough work for the period of my my period at Inria.
That's a good deal.
Yeah, that's pretty much good deal, but it works for at least 15 years.
Okay, so to be clear, when you say now it's manifold, it's instead of saying that X it's this deformation vector field, you say now it belongs to a Kendall.
Imagine that, well, yeah, I believe that for everyone in the room, using this representation from something that should be a shape is unfair. Okay. So since at that time we were already aware of that, the idea was to develop something model by model. Okay, so I give you 3 examples for the 3 examples that I showed you at the beginning. So typically for the fire propagation, the idea was to define some kind of functional using Manford-Cha functional. And then to try, as what people do in image processing, to use the gradient of the functional here, just the gradient, with a lambda, which is now a scalar, not an operator, just a scalar. And here you have the model. So you take the model, just the gradient, so you do some kind of gradient descent. You can't say gradient descent because this has a dynamics in itself. Okay, but typically, with respect to these dynamics, you add something which corresponds exactly to a way to diminish the function. And you put that like that. And then you work to prove that it works. Because there is no theory for that, so you show that actually the error between the two systems, should go to 0. Okay, so it corresponds mathematically to a stabilization problem of two systems, okay, that have different dynamics, but should have the same asymptotics inside. And so numerically, it works pretty well. You see, that's the so this system is called an observer, and it converges to the true value. We did that for the reaction diffusion problem, where again we put a correction here that take into account again the derivative of the Manford-Sharp functional. Yes.
On the left side,
Yeah.
the switch on free running observer.
So free run, when we say free run, it means. Oh, sorry. Yeah. It's from the. Oh, yeah. I didn't see that. So free run is in blue. Observer is red, and the target is black. Okay, yeah, the rest. What?
Yeah, exactly. You try to recover the evolution of the boundary, or you.
Yeah, you just try to recover the front. Okay, so
So you are not trying to estimate
the parameters.
the X.
But the x in that case corresponds to the front.
Okay.
For fire propagation problem, the state corresponds exactly to the position of the front. Okay, but what you are right is that for the reaction diffusion problem, then it's not the case. The state corresponds to the solution of this guy, which corresponds to a function defined on this manifold, and the observation is just the front.
Yeah.
So we use the same correction for the front, but we apply it to the reaction diffusion problem. So there is a huge reason that it doesn't work. Okay, but it works. The question is to be able to analyze it, to prove that actually this guy converges, which is difficult. Okay, and it's still open for us, but we prove that actually for small errors, it goes in the good direction. So we have a weak result, but at least we have a bit of result in B5. But let me show you how it works.
You told us that you are doing that case by case.
Yeah.
So what are your rule of thumbs to develop this kind of approach? How to raise
But the good point is that this guy is actually very low dimension to compute.
Yes, but this is for a particular model.
Yeah.
Let's assume that you have a model. What are the rules
Ah, so
It has to be.
no, but I don't want to lose my job, so I'm not telling you how I designed this guy. No, but typically the idea is to use the gradient of the functional to take the gradient with respect to let's say the good Sobolev space. So you take a Sobolev gradient of the functional in order to get something which is contractant for the dynamics. Okay, but for nonlinear dynamics, it's very difficult to prove that. Even for linear dynamics, it's very difficult.
You have to identify some sort of Lyapunov function.
For the nonlinear case, you identify the Lyapunov. For the linear case, you can use what we call observability condition and control theory to prove that actually you have contraction. And that's typically what I do when I do control theory for PDEs. Okay, because I started with control control of PDEs. But if I show you for the wave equation, which is linear, it's already a huge problem, and I can prove pretty much everything. But for this guy, it's super difficult for the linear system. Okay, but see, it works very well. So I'm starting with the wrong initial condition, and you will see that actually the reaction diffusion problem catch up with the data. So the data is here, okay, and then accelerate to catch up with the data. And when the data is before, it stopped to wait for the data. Okay, Okay, so with this type of situation, we were able to reconstruct maps for colleagues from DRX.
And just a question, because you showed us this noisy real data, but I don't understand what this is. It's a very noisy heart?
No, it corresponds to only, this is an atria.
Okay.
So it's just the upper part, left upper part of the heart. But this is also an atria. This is the same atria, a real one, and the one that, and the synthetic one. Okay.
How does that work when the cycle restarts? What would be the beginning of the next cycle?
So typically the excitation, so it depends. Somehow, if the excitation site is let's say it's not well chosen, then you re-excite from the wrong position, and then the observer continue to work. If you decide that in your parameters you put the position of the excitation site, then in the same time you retrieve the good trajectory and you estimate the position site so that when you recycle it will be good. But then it's even bigger to solve because then you have this situation.
But this is a trick to avoid going back, essentially.
Oh, for this reaction diffusion, you can't go backward. For the econal system, you can go backward. For the reaction diffusion, you can't go backward. The same for the mechanics, where typically, again, we put some kind of correction where we use the observed surface. And here it's pretty difficult because here you typically have a kernel which corresponds to a gradient descent with respect to a particular subsurface. Here, what I want to show you is the example is that typically the model will converge to the segmentation. Okay, so you start in orange on the wrong position and you converge to the good solution. And typically with real data on a pig heart, at the end you get something which is a model. So here you have the full model that is running, but actually in adequation with the data that we have. Okay. The problem for this method is that you have to design it case by case. Okay. Analysis is difficult and you lose the covariance. So you don't have a quantification of the uncertainties because you lose typically, you know where typically you are looking for some kind of minimum for the value function, but you lose the shape of the value function somehow. Okay, so that was so the idea was to do that on manifold, and that's the end of the talk. And typically, the idea with Gaël and Damiano Lombardi, which are also researchers here at LGLN, is to extend the ideas to manifold. So the idea is to define. So we did that by starting at the discrete time level. Okay, so everything is in discrete time. And typically the idea is to decide how we take into account the model error. So this guy that was that we don't know. So the idea is to say xn plus 1 should be the map phi of xn as before, but then you perturb this map by computing some kind of exponential path with this perturbation. Okay, so the perturbation here is in the tangent space of this. So, and the idea was to try to follow the same theory for that. Basically, the message is that under suitable condition, we are able to generalize the theory. So typically the suitable condition is that for general manifold, we need something which is Cartan-Hadamard, so something where, so typically not very well, it's difficult to encounter a Cartan-Hadamard in the situation that we are looking at, but that's the problem. Okay, so typically it should be complete, and typically we have non-positive curvature. There is also a possibility to prove part of the things here by looking at bounded manifold. But typically, under suitable condition, the idea was to define the things like that, where basically the value function now is just the solution of the same type of problem, but here you replace the norm by Riemannian distance here, and in the half convolution you replace here by a distance here.
In your situation, what is a noise model? In fact, because it's, you need to say something about
So for
the stochastic.
okay. If you give me 15 minutes more, then I can link to the stochastic. But I actually what I choose to do is to not talk about stochasticity here, but actually it's related. But to relate it, we need to go a bit further by doing some small noise. Yeah. No, you're right. You're right. Okay, I will try to answer the question for the stochastic model here. But typically here, what you do is you say that it corresponds to the limit for small noise of additive stochastic problem in the sense of the geodesy. Okay. Maybe it will be so. The idea is to solve. Sorry. To solve this guy. This is an half convolution. If you choose to solve this guy as a AGB solution on a manifold, you can do it. Actually, there is the same Hopf-Kohl transformer. Then, so you can have some vanishing viscosity version of that, where you see that you put some kind of Laplacian. So it will be not a Laplacian here, but a Laplace-Beltrami operator on the manifold. So the type of noise that we expect is that typically it's a noise where typically when you do Ito, you get the Laplace-Beltrami operator. Okay? And actually, I think at the end of the Gaël thesis, we will be able to justify this completely. But that's the spirit. Okay, let me just show you some examples. So one example to try the Mortensen estimator is to keep the dimension low again. So we do that on the sphere. So for the sphere, you can have any type of dynamics that you want. Actually, we decide to have this kind of nice time scheme to stay on the sphere, and we take something which is actually less complicated than that. We're just taking some kind of very simple slope. And typically, let me show you how the value function works. So you start with a value function. So that's the value function on the sphere, okay? And you start from the x0 hat, so your guess here. And the observation, total observation again, to simplify the example, is here. So then you take, first step, you take into account the observation. So you go there. And the value function changes because it takes into account the fact that you add one observation, okay? So it shrinks around this point because you have more confidence that you are here, because you take into account the observation. So if you remind that the value function gives you a way to quantify the uncertainty that you have less uncertainty, okay, because you have one observation that you have taken into account, okay? So that's after one correction. And then you predict, okay, and the way, you predict. So you predict, you first apply the model to compute this quantity. So it's the same value function where you follow backward the characteristic of the dynamics. So it moves here. And you take into account the half convolution to unshrink the uncertainty quantification. Why? Because you have error model. So since you have error model, your uncertainty increases. And so you get something like that. And that's your new prediction. Okay? And to solve that, you have to solve heat equation typically on the sphere, and we do that by computing the spherical harmonics on the sphere. So on the sphere, it's okay, and then it's very difficult. Let me show you.
The x and the y are living on the sphere?
Yeah, so it's a full observation case. So I'm cheating a bit, but now I will show you a partial observation. So that's still a full observation from Gaël. So you start from here, and you want to pursue a trajectory that is here. Okay, and that's the isoline of the value function. The 1, 2, 3, 4. Okay, and you see that you have conversion. Okay, depending of the parameter, the conversion can be very fast, because you have total observation. So if I want to change the parameter, I can tune it to go very fast to there. But the idea was to show how the asymptotics goes on.
And just in free run is what
Free run is that you do nothing. You start from here and you do nothing.
And in that situation, what is dynamic?
Well, yeah, again took some kind of vector field here to follow with the scheme that we showed before.
Yes, so in the first slides, you mentioned to have non-positive curvature.
And it's not the case. Yeah, no. Yeah. No, so the proof is for non-curvature, and basically and typically for the inconvolution part, typically it works for any bounded manifold case. So the sphere works. But then the question of
So you can positively curve
and still have a bit of hope. But I'm just
because you use convexity.
no. Yeah, the problem is that in that case you don't have the convexity.
The local convexity.
Exactly. So
when delta t goes to 0, we get convexity of in the internal distribution, right?
so typically in the Cartan-Hadamard case, you can use convexity arguments. Yeah, exactly. So in all the other cases, you can't use the convexity arguments, but it doesn't mean that the value function can't exist. There are other cases where you have non-convexity and still you have a minimum, and you can pursue the value function. So the inconvolution doesn't need the convexity to work. You need compactness and continuity.
Sure. But then if you want to prove the convergence.
Yeah, that part we don't know.
And then my point is, okay, when delta t goes to 0, maybe you can gain something. And
Yeah, but then you face the same type of. At the end, you will pay it in the sense that you still need a numerical analysis results saying that even delta t goes to 0, the number of time steps increases. So it will be what I believe is that the good result should be on the continuous case. But it's true that for one delta t, proving at least that we have existence of the algorithm could be done like you said. But for the asymptotic convergence, I believe we should go one step further. So it's still completely over. So you first need to go to the continuous case, proving that it works on the continuous case, and then going back to the numerical analysis case.
Because maybe there is a discrepancy between the continuous model and the time discrete model. If you want to put in question.
From my experience, all the results are harder on the discrete level when you want to go to the convergence. But okay, this case where we have partial observation. So partial observation here. Here we have an observation of the longitude, so it works. You see the trajectory converges. Here we have an observation only on the latitude, and it doesn't work because the trajectory here, the difference between the two trajectories is the longitude error, and so you don't see. And you see that the value function quantifies your uncertainty because here, even if it shrinks in this direction because you have observation, it doesn't work on this direction. It remains big on this direction. Okay, that's very okay. We can do quadratic approximation of this Mortensen filter, and in that case, we prove a version of what is called extended Kalman filter for manifold, which is an open problem for edges. There is a lot of try. I believe that here with Gael and Damiano, we have a way to actually justify one version with respect to the others. And there is the version with the additional term that we like very much, but I will skip that. Does it work on the shape manifold? The only thing that we need, for this last algorithm to work, we just need exponential, log, and parallel transport to simulate this quadratic approximation version. Okay, so as soon as you give me a manifold with x log and parallel transport, then we can do something to assimilate shape data. So we tried that recently on a shape manifold in a very simple version of shape manifold where typically we can go back to the sphere because we have a result on the sphere to start with, but really the idea is then to generalize to other manifold. So that part you know it pretty well, and I will conclude with the last results from Gaël that I believe are super nice. So free run, observation, and then you see the fire, okay, targeting the real one. To compute this guy, we divided the state in three. So total observation again, but we divide it into three components: the barycenter, the length of the curve, and then the curve in the shape manifold. So this gives you the evolution of the length, okay, in log scale. This gives you where the barycenter should be with the value function reconstruct from the covariance. And this gives you the modes of the shape computed from the covariance operator that we developed. So you compute through time a covariance operator, and from this covariance operator, by spectral analysis, you get the shape variation. Typically, here we don't do the. Usually, we put all the shape of the space.
So here you observe, okay, just because.
Here you observe everything.
Okay, but you observe the boundary.
Yeah. And the model is the boundary also.
And what is the noise on the boundary? Okay, you observe perfect. What?
No, you put noise on the boundary. So again, you need a model of noise, and the model of the way we model the noise is by computing the true trajectory, and for each time step of the true trajectory, we perturb it by a random field and do on a delta t scale an exponential map to perturbate the boundary.
Yeah, not just to have some feeling about what is the when you observe, okay, for the observation
Right.
of the typical front, what is the uncertainty for the observer?
So typically the true trajectory is something like that. Okay, where we put, so that corresponds to no noise. So that's not the true trajectory, sorry. That's the dynamics of the system. No noise on everything. Then from that, we add a bit of model noise. So the model noise gives you something like that by using the exponential mapping. Then we record the frontier as observation, and we perturb the observation with noise so that you get something like that.
Why you have this level of no?
Because there is one level for the model and one model for the observation. There is error on the model and on the observation. And then you start from a wrong initial condition with something that, if you let it free, should give you something like that. And that what it gives you is actually, it moves to go back to this guy. To go back actually to this guy, not this one. It will try to filter the noise here, but to keep the noise here. Okay, that's why the two covariances here play pretty much an inverse role in the formula that I show you, in all the formula that I show you. I know that it's a lot of formulas, but basically the two covariances enters in the algorithm in ways that somehow you try to filter what is here and take into account what is here. That's why typically on the sphere, what I give you on the sphere for that was, if you have here, you shrink the uncertainty, but when you are, after that, after the characteristic, you re-expand the covariance. You have model error, so you re-expand your uncertainty. You have observation, so you shrink your covariance. Okay, and everything is based on the fact that you have a guess on the level of noise that you expect. Otherwise, it doesn't work. Because so you know basically the amount of noise that should be here and should be here by their covariance and their.
But okay, I don't
Yeah.
want to ask too many questions.
Okay. Yeah. So
Let's see.
no. Yes. I finished with this last last example. Sorry. Yeah. Okay. So the conclusion, typically. So I love dynamic programming approaches, and I think it's that the best answer to the question, why are you doing that? Still because there is still a lot of open question on this, about the formulation that we can have on very general system, about the theoretical open question on that, about the numerical aspect on that, about the asymptotic question with the link with the stochastic version of the same problem. We believe that it can work for shape analysis, for data analysis with a shape problem. What we need is a remaining structure for the shape space. And I believe that typically it could work also for other situations where typically you have data on manifold space. So one question that we're looking at now is if you consider a model where you have densities, typical densities, you won't have, for example, Wasserstein structure on this density, then you can do the same using the metric that you can put on the Wasserstein system. That's typically a question that Gael is looking at for now. Thank you. Ouais, j'ai été.
So you have a lot of questions here. What are the main bottlenecks? So what are the most important questions for you, and what are the main bottlenecks, and what are the challenges in this field?
But I believe that here is pretty much well summarized.
So if you have just one question to give me the answer, what should I answer?
Yeah. No, but okay. If I want really to give you one open question that can be of interest for you, if you want to do that on Wasserstein space, okay? But why not? Okay. What should be? Do we have at least existence of the value function for probability space with bounded second order moment in the Wasserstein space? Do we have enough structure in the Wasserstein space to at least define the object? That's typically one open question that is looking at. Okay. This is a good one. One, or if you want another good one, is typically what we are looking with Louis-Pierre Chantron at the moment with a PhD at ENS, where we try to actually prove the convergence of the quadratic approximation to the solution in the case we have enough regularity for the dynamics with the Hessian to exist. So we know cases where we have enough regularity, and then we need this contraction argument. But that's difficult because we need to follow some kind of Hessian property on the viscosity solution of the HGB, which is a difficult subject. Yeah.
But numerically here, in fact, you are doing this some kind of quadratic approximation, or in this setting, in fact, you still have the same numerical bottleneck you had in the RS.
Yeah. So
Because,
you're right. So typically, HGB, we will never do that for shapes.
Yeah.
Okay, so HGB we forget. HGB just a way to set up the problem. Then we have the quadratic approximation. So in the quadratic approximation, you follow only a covariance. A covariance on a shape in 2D or 3D remains okay in terms of complexity burden, because it will be in 2D, so 1D problem. So basically, with 10,000 points, you can still store the covariance. Okay, so it works. And in 2D, we developed some H matrix version for storing the covariance that gives you opportunity to store the covariance up to millions of degrees of freedom. So there is hope for that. But still, I believe that it's too much. So then I developed one thing that I didn't talk about, which correspond to what we call covariance reduction. So typically, covariance reduction corresponds to actually projecting the covariance on a subspace of let's say, a slower dimension. The problem is that to follow the covariance reduction through time, okay? But that we can do. We can do it. So that we have done articles showing how you can continue to follow the covariance reduction on a specific subspace with the time evolution of the problem by just actually pursuing how the space evolves through time. So this works very well, actually. And typically the message is that for all people who do a virtual twin now, because a lot of people who do model, what they say is that I want to do uncertainty quantification, what I should do is project my dynamics on a slow dimension subspace by doing typically statistically reduced order spaces approximation, like for example Albert Cohen here, typically, and at the end you get a small dimension space for the dynamics, and on that you do the full problem. What I believe in is that you can continue to have the full dynamics if you do the reduction only on the covariance representation. And then you get some kind of dilemma between what they do, which is a bias stability. So they have a bias, but more stability because they have the full covariance on the reduced space. And me, what I do is that less bias, but more instability potentially because I reduce the covariance. So I don't have the uncertainty everywhere. Okay. And and you can prove that this dilemma can be nice in certain cases. So it's the same classical dilemma that for any statistical problem. Okay. So so the answer for your question is that with reduced covariance, you can have formula like this, and at the end with again we will have something like this, where actually here there is one more step which corresponds to a projection of the covariance operator on a subspace that is evolving through time. The subspace should move with the time. Otherwise, you don't see anything.
And I was curious about the fact that, okay, there is no way about using some particle filtering point of view, or?
So the particle filtering point of view corresponds to the stochastic to the stochastic setting.
Just the covariance, but okay, you have also.
Let me just show you. Yeah. Okay, so typically, if you want to do particle filtering, you can put something like that. So you get the same dynamics, and but here now you get really a stochastic version with additive noise. So this version is not in the manifold, but it could be, I believe, I'm not sure, it could be partially extended to the manifold case. So that's typically what we do when we do particle filtering. And in particle filtering, what you compute is actually the conditional density with respect to the observation. Okay. Then you prove that actually the conditional density follows with a bias formula, some kind of law like this. So exponential here, and then you have a convolution. Okay. What I show recently, so it's a paper now under review with Sebastian Reis and on this subject, where basically the idea was to prove that this density, which is unnormalized, so the density corresponds to the normalization of this guy, this density here that follow this actually tends when epsilon goes to 0 to the value function that I compute. So all the value function theory that I develop correspond to the asymptotic limits for scaled small noise in epsilon. Okay. So then the question is, why are you using the value function instead of the density? It's a good question because nobody care about the cost to come. So I love to care about something that people don't care about. But more interestingly, I believe that for situation in infinite dimensional system spaces, even if the problem with the value function is difficult, it's less difficult than actually the stochastic problem in the infinite dimensional case. The infinite dimensional stochastic filtering problem for linear system is very well known from Alain Ben-Soussan in the 70s, but remains super hard in terms of theoretical development. If you stay on the deterministic point of view, you need some kind of solution of HGB in infinite dimensional space, but still I believe there is more space. And I believe that there is more space also for the extension in the manifold. But okay, but just okay, that's the path that I want to follow. But,
Thank you. Thank you for all the questions.
And so if I can ask you a question, is that, okay, in all of your talk, basically you abstracted away the dynamical system, especially for the heart, etc.
Yeah.
And I'm wondering how sensitive you are to the quality of the model. You know, I'm asking this because my impression in our field, we are trying to do data with model, and with PDE models, I always get the impression that on the shelf you have either very expensive and cumbersome real physical solvers that come with guarantees, and very appealing like video game solvers, like projective dynamics, stuff at SIGGRAPH, which is super fast, easy to implement with Tai Chi, etc. But okay, but maybe it's not good enough to trust it to fly a plane. But my impression is that in our field, since we have data, we say, it's good enough. And so I'm asking you in practice, what will you...
No, it's a huge question. It's really huge question. So from the world that I come from, so typically where you have like model centric, you spend, I would say, half of my career is about developing model for the heart. So the modeling part. So when I see people using P1 finite element with like a very cheap model and showing to medical doctors a heart that is moving, and when I show the same heart moving, but I say here I have the good physics, and the doctor say actually I don't know about the physics, so I don't care about what I care is just that the thing is moving, then okay, I'm pissed off. Okay, so typically I come from I have a huge bias on that. The fact is that in data assimilation, you have ways to actually to catch up with model errors. So I even give an argument to the people who actually don't do a good modelization, good modeling, because then they can say, yeah, you have some kind of a model error, and that's it. So the point for you is to be cheap from a modeling point of view. And it's difficult to answer to that question. Still, I believe that I've seen many articles where people, when they do then parameter identification, so they do this kind of stuff, they add a bit of model error, and then they find parameters. And they give parameters in their article. And they say, you see, one day we will cure the world because we will give parameters for the sick heart to doctors so that they can quantitatively assess your heart. Okay? The parameter values that they found is 10 to the power of 3 the value that we have in our models. So what is the meaning of what they sending to doctors? So as soon as nobody is looking at the value of the parameter for real, as soon as there will be no guy who actually opening the animals to say no, the value function should not be 1,000 but 1, they will gain the game because they will be cheaper and faster. Yeah, maybe. I believe that for the parameter and for the predictivity, I've done one conference like last year where I was with people like that, and when we decided to share the table ronde, they say, okay, Philippe, you will talk about predictivity because we never talk about predictivity ourselves. I was like, why are you doing model then if you don't talk about predictivity? Everything is about predictivity. Like that's why I'm showing that. Is that the question is that this model, without the data, should predict something. So at some point, I should stop to use the data to predict the behavior in the future. What I believe is that all these people, since they have cheap model, when they forget about the data, the prediction is completely wrong. Okay? But still they have one argument because they say, yeah, the same with the weather forecasting. When you stop having data, you don't predict the weather. You see, poor weather here, okay. So it's a never-ending problem. So I believe in models for sure. Yeah, that's my bias.
About this, when you show these free-run graphs, you always put the free-run at 0, but you could put it at any time step, I guess, to see the evolution, the prediction. No?
So
it's related to what you just said, like that you are continue to be correct even if you don't use your data anymore after some time.
Oh yeah.
But you don't show this anymore.
No, well, for the example here, but typically what we try to do in real situation is then to stop assimilating data and continue to predict and then show that the error is actually small for a certain time in the prediction. That's what we are trying to do when we do real stuff with the medical doctors typically. So the idea is to say you have a time window on which you do a data assimilation and then you predict on the rest of the time window.
Sure. Okay. So I was seeing.
Yeah, it corresponds, and this corresponds to the free run. Yeah, and when you stop, it corresponds to a free run starting at that time. You're right. Completely right. Yeah.
Okay.
But still, but I mean, in many situations it doesn't work.
Okay.
No, I mean we do sciences, so typically sometimes I still believe that even if we are wrong, because we are all wrong, but I'm less wrong than people with a bad model.
Sure.
So I can't argue on the fact that I'm right. I'm wrong. The question is how wrong I am in terms of models, and I believe that it's important. That's still an important question.
Yeah, another question. Because from the beginning, when you go from continuous to discrete,
Yeah.
it looks like you are using a Euler scheme.
Yeah. But
have you thought about it?
No. Actually, yeah. In practice, I barely use a Eulerian scheme.
No, Euler. I mean.
Yeah. But I mean, I choose to. I say, for example, you can use a Eulerian scheme, but you can using pretty much any scheme that you want.
Okay.
The question is that from this to be abstract enough, what you need is just to be able to write your dynamics as xn plus 1 equals pi of xn. So you just want to give something that corresponds to a one-time step evolution. But that is general enough to enter any discretization. Okay.
Okay. No, because when you
and this could depend of n. Huh? You can do time adaptation. You can do pretty much everything. It was already quite heavy in terms of notation, so I decided to kill this guy.
Okay. No, because when you showed this prediction correction, it's featured by the.
No, but you're right. So, for the numerical analysis point of view, the data assimilation algorithm remain even if this, for example, is second order accurate, the data assimilation scheme will be first order accurate with respect to the continuous, because somehow this splitting scheme is only first order accurate. But I choose to have this splitting formulation because of Wikipedia somehow. Because in the 60s, Kalman says that a good data assimilation algorithm should be that. So the idea was to design the time scheme of the data assimilation procedure so that in the linear quadratic case, I get this exactly. And in nonlinear cases, I get an extension of that with the same structure where you use the data when they are available and you predict when you don't have data. And then I think it's a very good idea for engineers because you can say, just follow your model when you don't have data. And when you have data, if you are able to have an idea of the covariance, then we can perform some kind of corrections. The hard simulation for the pig is 12 hours of simulation. Okay, so I'm wrong and I'm slow. Okay, but the data assimilation procedure like that was, I would say, 20%, 10 to 20% more than the 12 hours. So the data assimilation part that I'm adding is less expensive in most of the situation than the model itself, because for this type of very heavy model, actually all the burden is in the model. And I think that's pretty good news. I don't know if I move to something where I have to do some Wasserstein distance, then it would be expensive in both configurations.
So to come back to your work on proximal step on manifolds.
Yeah.
I've seen that you have a step which takes the exponential map at some point.
Yeah.
Did you do convergence of this scheme? Because and will you take into account possible error that you made exponential definition?
Actually, so this is Gael. So this is what we are doing in Gael PhD thesis. So it's not even published. Okay, so typically the results that we have for now is that at least under strong assumption we can define the object. Okay. The question of convergence with respect to delta t, I believe, I'm sorry Gael, but I believe that we will not do it during his PhD thesis because it's really super hard. So at the convergence with respect to delta t, it's really hard. I'm still doing it in the non-manifold case, and it's pretty heavy. Okay, so I'm still okay. So I believe this is very new. So okay, this formulation is very new. And what is nice is that you have some kind of structure. Oh, sorry, there is an equal there. Okay, you have this nice structure, and convolution are nice even in manifold. You can have such kind of development. If you add a bit of stochasticity, here this is replaced by the vanishing viscosity version of the AGB solving this gap. So it gives you a bit of regularity. So for example, Louis-Pierre Chintron believed that we should avoid to go to this singular version and keep the epsilon version. But when you do that, then you do particle filtering. And then I'm doing what all the other people are doing. And then I'm cursed for the work that we... But no, I think it's a very good idea. Okay, you should be exhausted. I'm exhausted too. Yeah. J'ai tendance à me fatiguer moi-même d'ailleurs. Je vous comprends tellement.